For a 5-digit postal code, how many are possible if there are no restrictions of the digits? Well, 5 digits, so 1, 2, 3, 4, 5. And if we say no restrictions, that means each spot has 10 choices. Now these are codes, not numbers. So 10 to the 5th. Now how many are possible if 0 is not allowed to be the first digit? So the only thing that changes here is that you have 9 choices on the first one. And 10 choices on the rest. So 9 times 10 to the 4th. Question 7. A survey of 60 shoppers reveals that in the past week 20 bought toothpaste, 15 bought deodorant, and 8 bought both of these items. Well, if you notice the structure of this problem, it's a Venn diagram. So toothpaste and deodorant. And we know that 8 people bought both, so that puts 8 in the middle. 15 bought deodorant, so that puts a 7 right here. 20 bought toothpaste, so that puts a 12 right there. We know there's a total of 60. Add that all together, subtract from 60, and you get 33. Now part A says bought toothpaste or deodorant last week. Well, if we think about our picture, or means union. So if I was going to come to my picture and shade it, I would have shaded all of that bit right there, toothpaste or deodorant. So those are the numbers I want to add together. So I add together a 12 plus 8 plus 7, and it gets me a total of 27. Part B says exactly one of these things. Well, exactly one means only in one circle at a single time. So the 12 and the 7. Those are the only people who only bought, or who are only positioned in one circle at any time. So 12 plus 7 is 19. Question 8. 7 distinct points are marked on a circle. How many different triangles can be drawn? So if I draw myself a circle and then put on our 7 points, now a triangle needs 3 vertices, 3 corners. So if I look at this, if I start here, is there any point that I cannot go to? No, I can go to any of the other 6 points. So let's just draw a triangle here. So using 3 of those points, I drew a triangle. Now, is there anything special about starting at this one point here? If I picked one of the other points on that triangle, started, I could have gone through here. Also, I don't have to draw them to connect those points in a special order. So what this basically has told us here is, well, first of all, you got to have 3 different points, so no repeats. The order that you connect those 3 points in doesn't matter. So we're dealing with a combination. We have 7 points on that circle. We need 3 of them to form a triangle. So combination 7, choose 3. How many different outcomes are there if a coin is tossed 8 times? Well, draw out 8 blanks. We're tossing a coin 8 times. So on the first toss, the coin could come up heads or tails, so there's 2 choices. Each one of these tosses has 2 choices. Which gives me 2 to the 8th. The bag contains 8 red apples, 4 yellow apples. We're going to select a sample of 3. Sample, I'm not concerned about the order. I can't have repeats, so I can't pick the same apple more than once. And I want all to be red. Well, combination. I had 8 red to start with, and I need to pick 3 of them. Part B says there are no restrictions. So any 3 apples. Well, we had 8 red and 4 yellow. Combination 12, choose 3. Now part C says at least 2 must be yellow. At least 2 are yellow, so that means 2 or 3 are yellow. It means I need either 1 or 0 red. So it's the same chart like we did earlier. So combination 4 choose 2 times a combination 8 choose 1. That counts that first outcome. Plus, now do 3 yellow. 4 choose 3 times a combination 8 choose 0. Now the 8 choose 0 is not necessary because anything choose 0 is 1, and this is being multiplied together. Question 11. How many ways can the letters of the word turkey be arranged in a row if, in part A, there's no restrictions? Well, I look at the letters in the word turkey and notice that all of them are different. There's a total of 6 of them. So I'm going to put 6 different objects in a row. I could draw out 6 blanks and go 6 times 5 times 4 times 3 times 2 times 1. Or just realize the answer is 6 factorial. Now, part B says the first letter must be a K. So there's one choice there. Now there's no restrictions on the rest. So 5, 4, 3, 2, 1, or 5 factorial. Part C says the first letter must be an R and the last letter must be a T. So those last spot and the first spot have only one choice each. The other spots in between, no restrictions on those. Four times 3 times 2 times 1. In other words, 4 factorial. Now part 12 says, or number 12 says, in how many distinguishable ways can a row of 2 S's and 9 F's be arranged? So if I want to write out an example, SS and then all the F's. So here's my 2 S's and my 9 F's. So that's one arrangement. Now notice we have repeats. So if I shuffle an F with an F, it's still the same arrangement. So this is the Mississippi type problem, distinguishable rearrangements. Well, I had a total of 11 objects, so it's 11 factorial. How many repeats? I have 2 S's, and I have 9 F's. So there is a method to solve that. Now there's another method, in other words, that will also solve this problem. If we think about a row, in other words, put in 11 blanks, and I come in here and says I have 2 S's. Now, when I select the positions for the letter S, so in other words, take that row of 11 blanks and pick 2 spots for the letter S. If you pick spot 1 and spot 2, it's the same thing as picking spot 2 and spot 1. Because of that, in other words, there's 11 positions, pick 2 for the S. Since the S's are identical, it doesn't matter the order that you pick those positions in, the S will be in those spots. Now once the S isn't placed, now we place the F. There are 9 F's to be placed. We had 11 to start with. We used up 2 spots. That means there are 9 spots left. We need all 9 of them for the letter F. Now notice this picks the S first and then the F. Nothing in the problem says I can't do it the other way around. So if I wanted to, I could have come over here and says, well, I started with 11 spots. I need 9 of them for the letter F. And then the remaining 2 spots go to the letter S. What we have here is, in essence, 2 different styles of working the same problem. One, looking at it as a distinct rearrangements, all the letters in a row, shuffle them around. The other method is to look at it as picking positions for the letters. Both methods get you to the same answer. It's just different styles of working the problem. Box contains 4 red and 7 green marbles. 2 of them are drawn without replacement. How many ways is it possible to get 1 red and 1 green? Well, of the 4 red, pick out 1. Of the 7 green, pick out 1. We're not concerned about order. We're not doing replacements, things like that. Now notice, since these are combinations of choosing one item, we could have just said in here 4 times 7, and that's equal to 28. Part D says at least 1 is red. Well, of the 4 red, pick 1. Of the 7 green, pick 1. But that's exactly 1, so now we do exactly 2 red. So that gives me at least 1 red. Part C says both are to be red or both are to be green. Now once again it's the or. So we do both being red. Well, that's a combination. 4 choose 2. I could do 7 choose 0, but that's 1. Or both are to be green. So looking at this right here is both red. This right here is both green. Now when you have an or statement, you should ask yourself, do we need to subtract off anything? In other words, can we have both red and both green at the same time? The answer is no. So there's nothing to subtract off. These two outcomes, these piles, are disjoint. We have a box that contains the following balls. And how many ways can a sample of 3 be selected if all of them are to be red? And that's part A. Well, sample, that means we're not concerned about order. We're picking 3 of them. We look back at the balls, and there are only 2 red to start with. Well, if we need 3 and we only have 2 to start with, the answer is 0. Part B, we want them all to be the same color. That means all 3 red, all 3 green, all 3 black, or all 3 blue. Now, we only have 2 red, so that doesn't happen. So we start off with all 3 green. Well, there's 4 green, we need 3. We don't need any others because our sample's complete. All 3 black. Well, 6 black, we need 3. Or all of them blue. And so that gives us all the different ways that they're all the same color. How many ways can we get exactly 2 of the balls the same color? So if we think about this, this is 2 red and 1 other. Or 2 green and 1 other. Or 2 black and 1 other. Or 2 blue and 1 other. In other words, I sort of make a chart from similar to the fashion of like problems 1 through 4. So this is what I'm looking for. So 2 red and 1 other, so combination 2 choose 2. Now the 1 other, we have 4 green, 6 black, and 3 blue, so 4 and 6 is 10. That means of the other 13, we need 1. Or 2 green, combination 4 choose 2. Count the ones that are not green. 6 and 3 is 9, and 2 more makes 11. Or 2 black. The 1 other. There are 9 that are not black. And then 2 blue and then pick one from the 12 that are not blue. Part D, we want more red than green. So we're picking a sample of 3 and we want more red than green. So this one is easiest done with a little chart. So red, green, and other. Now looking at red, we have 2 red. Green, we have 4 green. And there are 9 others that are not either one of those. So I look back at this and say, okay, more red than green. So if I have 1 red, I can have 0 green, because I have to have more red than green. And at this point, this means I need 2 of them that are not either one of those colors. Or I could have 2 red and 0 green in one of the others. Or I could have 2 red, 1 green, and nothing else. Now we stop at 2 on the red because red only has 2 to start with. So once we have our chart figured out, this isn't too bad. Combination 2 choose 1 times the combination 9 choose 2 plus the next line, combination 2 choose 2 times the combination 9 choose 1 plus, on the last line, combination 2 choose 2 times the combination 4 choose 1. Now notice I didn't put any of the combinations that involve the zeros because you can have them, but they're not necessary.